Okay, so we have our test on Thursday. Tomorrow we'll go through another example of using the geometric series method to come up with the infinite series. Next year, so this only applies to the 4 students who are back next year. So this is the degree path for mechanical engineering, and you have to take. Let me get my thing here so I can point. So this is Calc 1. That's 173. That's 174. I've decided we're going to do that next year for the seniors who want to take another math class. We'll take linear algebra, and we'll do that in 2 semesters. So normally you have study session. We'll take part of study session. So I'll do like two 30-minute classes a week instead of 2-hour, 3-hour class, whatever. It'll be equivalent of, it'll be kind of like you did statistics last year. So I've ordered my book to look at the one they use at Virginia Tech. So they usually take this your freshman year, spring semester your freshman year. You can also take multivariable calculus. And there's somewhere here is differential equations. I don't know where it is here. Intro to differential equations. For them to take differential equations, you've got to have taken multivariable calculus and linear algebra. Take a linear algebra, you've got to take Calc 1. Then you also take this physics, which is the calculus-based physics. That's kind of the sequence of the way it works. Statics is like Newton's second law in equilibrium. Then you have to take dynamics is Newton's second law with things moving. Apparently got to take an engineering statistics class. And thermofluids is kind of like thermodynamics, fluid mechanics. What else do you have to take here? System dynamics is kind of looking at spring mass damper systems. We in chapter 13 we talked about spring mass systems as far as physics is concerned. This is just a lot more detail. And then you've got to take this is an intro to thermofluids. Then you got to take thermodynamics, fluid mechanics, heat transfer. That's what we've been talking about in the last couple of weeks. Heat transfer. Anyway, I was just showing you, I brought this up to show you guys where linear algebra fits into the whole thing. But actually, of the 3 that we were looking at, linear algebra, multivariable calculus, and differential equations, this probably has the widest usefulness as far as future careers, because a lot of the things you learn here relate to computer science and as well as math. Okay, so what we're going to do today is we're going to go to chapter 10. I'm going to give you a brief overview of section 1. If we have time, we'll cover it again. We'll come back and cover it, but I want to skip over it, most of it for right now, just because it takes a while and I want to make sure that I get to the stuff afterwards. So I'm going to, on one page, I'm going to give you my summary of section 1. I'm not going to assign any homework out of this section first, but basically what it's talking about is conic sections, and conic sections are things like parabolas, ellipses, hyperbolas, and a special case of ellipses is circles. And have standard forms that you can put them in, and you can then use those standard forms to plot ellipses, hyperbolas, and circles, and parabolas. So the standard form for the parabola is y is equal to a times x minus h squared plus k. And you probably have already seen that before, even if you haven't ever taken anything to do with conic sections, because that's the form that we've used to plot them in pre-calculus. So A is kind of like a stretching term. H and K are the indices of the vertex, and it's a what we would call an explicit equation because we can solve directly for y with one equation. And depending upon, and there's also, you can also have a parabola x is equal to a times y minus, I don't know what if we'd use h and k or not, but probably not. But you know, you can have a parabola that looks like that, or you can have a parabola that looks like that, depending upon whether you solve for x or y. Ellipses look something like this. They have x minus h squared over a squared plus x minus or y minus k squared over b squared is equal to 1. So that's the standard form for an ellipse. And remember what an ellipse is. It's is you have, so let me just kind of sketch. These are my sketches of the parabolas. But if you had an ellipse, and let's say the center of the ellipse are the coordinates h and k. This would be the h coordinate, and this would be the k coordinate. And then you can kind of draw a box using the A and B values, and that gives you kind of the outline of where the ellipse goes. And the two of the key points for ellipses are they have focus points, foci. And it turns out there's also, well, yeah, I'll come back to this. I don't want to get too carried away. As far as a hyperbola is concerned, you have two forms. You have x minus h squared over a squared minus x minus or y minus k squared over b squared is equal to 1. And the other form would be where you have the negative in front of the x. So you'd have negative x minus k squared over a squared plus y minus k squared over b squared is equal to 1. So where the signs are, well, for one thing, the difference between this and an ellipse is that one of the terms is positive and one of them is negative. I don't know why it looks like I wrote cubed there, so it shouldn't be cubed. Let me fix that. So depending upon whether you always have positive 1. So if this is positive 1, this is negative, this is positive, you get a hyperbola in one direction. I can't remember which ones go which way right now, but you could have a hyperbola go this way, or you can have a hyperbola go that way. And that's determined by which one of these terms has the sign. So what usually you do with hyperbolas is, again, you have a center to the hyperbola, and you have a box like this that's defined by these values a and b, but instead of having it inside the box, it's outside the box. And the way it works is you draw straight lines through the corner of the box, and the vertices for the hyperbola are on either this side or that side, depending upon whether it's going this way or it's going that way. In this case, it's going this way, so these lines that cross serve as asymptotes for the hyperbola, kind of like that. So again, by putting them in standard form, you can set it up so you can sketch these things pretty easily. So hopefully we'll have time to come back and talk about the details about that. But that's, and the two things also is these are implicit equations. So we can't solve for y or x. We could solve for y or x explicitly, but then we'd have a plus or minus a square root. And so you'd have one solution would be up here and one solution would be down there. If you explicitly solve for x or y, same down here. The question is there any way to find the slope of the tangent line to these curves without explicitly solving for x or y? So that's how many people have seen hyperbolas in this form in previous classes? Maybe, maybe not. It's been a while. So we're going to go to section 2 now here. So section 2 is titled Plane Curves and Parametric Equations. So these are plane curves, are just curves that are in a plane. So they're two-dimensional curves. And what we just talked about, which were ellipses, hyperbolas, and forgot circles, are when A and B are the same. In terms of their ellipses where A and B are equal to each other. But those are plane curves, ellipses, hyperbolas, parabolas. We're going to now talk about just in general plane curves. And we're going to use what are called parametric equations to define the curves. We've done this in physics because the equations of motion are parametric equations in time. So you have y as a function of t and x as a function of t, and that's what you introduce an additional variable called the parameter, which helps you define x and y separately. So you have a lot of times you can have a curve. We might have called that a function in the past, but curves can be functions, or they can just be, they don't have to be functions. They can just be any line in two-dimensional space. And there are usually two ways to do it. One is in terms of rectangular coordinates, and one or equations, and one is in terms of parametric equations. So for example, a circle, so we're going to do a circle in both parametric and rectangular form. So the rectangular form is the one we're used to, which we'd have x squared plus y squared equals 36. So that would be the equation for a circle. It's an implicit equation because I haven't solved for x and y directly. I've just got them both on the same side of the equation. An equivalent parametric form of this curve, if I drew this curve, what would it look like? It would look like that, and then you'd have a circle. So this is a circle with a center at 0 with a radius of 6. So this has a radius r equals 6. The parametric form would be x is equal to r cosine t, and the y coordinate would be equal to r sine t, where t is between 0 and 2 pi. So you can kind of see what would happen here. Let me just show you how you would plot, or how you would figure out the coordinates of a parametric equation, how you would do that. So let's, where did my table go? Oh, there it is. Okay. So instead of having x versus y, you'd have t in the first column, you'd have x in the second column, y in the third column. And you might start out at 0, pi over 4, pi over 2, pi, let's say 5 pi over 4, 3 pi over 2, 2 pi. So if I use this equation, this is r cosine t, this is r sine t. What you would get is 0, 6 times the square root of 2 over 2. You get negative 6. No, you get 0, sorry. You get negative 6. You get negative 6 square root of 2 over 2. You get 0. You get 6. And that should be 6, not 0. I don't know why I put 0 in. This is 6. And if you plugged it into the y equation, you would get 0, 6 times the square root of 2 over 2, 6, 0. This is in the third quadrant, so it's going to be negative 6 times the square root of 2 over 2. That'll be equal to negative 6, and that'll be equal to 0. So all I've done is I've taken the sine and cosine of these various values of multiples of pi. So the cosine of 0 is 1. So you take 1 times 6. The radius is 6. So you get 6. And pi over 4, the cosine is square root of 2 over 2. So you multiply 6 times the square root of 2 over 2. Cosine of pi over 2 is 0. So 0 times 6 is 0. And you can see what I'm doing. I'm basically plotting. What I'm doing here is I'm plotting. Let me just show it on the diagram. I'd be plotting this point. I'd plot that point. That's the next one. I'd plot this point, this point, this point, this point, and back to the beginning again. And you can see they all lie on a circle. So this is the parametric form of a circle. So, and they're both rectangular forms and parametric forms of lots of different curves. Okay, that's what I just explained. Okay. So, yeah, we've done the t versus, that's what this is showing. What we would do here, we would have, it would be 0, it would be actually 6, 0. In the case of a rectangular plotting, we just have x and y. And so how would you find those? Well, one way you could do it is you could solve explicitly for y and plug in different values of x. If I solved explicitly for y here, I'd get y is equal to plus or minus the square root of 36 minus x squared. And so then I could pick values of x. So if I go over here with that equation, y equals square root of 36 minus plus or minus that. The plus part's going to be the top half. The negative part's the bottom half. And if I plug 0 in for x, I'll get the square root of 36, which is 6, which is exactly what I go over here. Except that's actually wrong because that's this point. That's this point. Okay, those are the two coordinates. And if I put in x equals 6, I'd get the square root of 0, which is 0, so that's that point. So there's just different ways of solving for the same set of points if you plot them in the rectangular coordinate system. So both of them, the rectangular equation we plot in the rectangular coordinate system, but the parametric equation we also just, the t is just a way of generating x and y. Here the equation is used to directly find y when you specify x. Now you can take parametric equations and you can make them into the XY equation. Okay, and that's called, doing that, that process is called eliminating the parameter, which is t in this case. Eliminate the parameter t. So what you need initially is some kind of equation that defines x in terms of t. So let's say we have 3t squared plus t, and y is equal to 1/2 t. So these are, I don't know what the function looks like. I don't know what the curve looks like. I just made these up. So this is the parametric form. What if I want to get, how do I get to the x, y form basically? So what I want to do is I want it in the rectangular form from the parametric form. So the way you do it is you solve one of these two equations for t and plug it into the other equation. So it's just basically like eliminate substitution. So in this case, because y is equal to 1/2 t, it's probably easiest to solve for t by multiplying both sides by 2. So I get t is equal to 2y. And then I can plug into my original equation, y is equal to 3, but instead of t, I put in 2y. And then I simplify. So I'd get 4 times 3, 12, y squared plus 2y. Okay, so that's the rectangular form. I could have done it the other way. Well, not quite so easily because I don't have, I'd have to use completing the square probably to solve for y instead of for x. But it's in rectangular form now because it just has x and y. So this is the rectangular form. Let's try this one that we just did a second ago. Well, I'll write it down on the next page. So let's go back to this one. We had x equals r cosine of t and y equals r sine of t. So if we divide both sides, let's solve this one for t. So we'll take the first equation, solve for t. So we'll get x over r is equal to cosine of t. Therefore, t is equal to the inverse cosine of x over r. Okay, so now what do we do? Well, if we go back to this original expression, draw a triangle. So let's say, well, we'll call the angle t. So the cosine of t is equal to x divided by r. So I'm kind of using like in trig substitution. I'm going to create a triangle from one of my expressions. So the cosine is the adjacent over the hypotenuse. So the cosine of t, which I'm saying is the angle, is equal to putting x as the adjacent side length and r as the hypotenuse. So from that, I can find using the Pythagorean theorem, I can find the opposite side, which is going to be equal to r squared minus x squared. So now I can then say that the sine of t, if the cosine of t is x over r, then the sine of t is equal to the square root of r squared minus x squared divided by r, the length of the opposite side over the hypotenuse. So then I can substitute that into here. The sine of t is equal to the square root of r squared minus x squared over r. The r's cancel out. At least those r's cancel out. Then you square both sides. You get y squared is equal to r squared minus x squared. And you bring the two variables to the same side, and you get x squared plus y squared equals r squared. And so that's your rectangular form. So we started with the parametric form. Use one of the equations, whichever one we wanted to do. It doesn't turn out to make any difference. I chose this one. this one. So I divided both sides by r, took the inverse cosine. That's what I'm going to, that's t. But I use this definition to define my triangle, find out the sine of t is equal to well, actually, did I actually, I did, yeah, so I did find the sine of t. I guess I really didn't need to do this part. I kind of did the same equivalent thing over here when I created the triangle. And then I was able to rewrite, I found out the sine of t, not t directly, but sine of t. So we really didn't need to do that. We just needed to take this definition, define our triangle, so that we could define the sine of t to substitute. So it's a little more. So that's called eliminating the parameter. You can always rewrite it. Okay. The other interesting thing about parametric equations is that you think from dealing with two-dimensional stuff. Let me go back one step. So let's say a line in 2D. Y is equal to 3x plus 2. So you might assume that a line in 3D is z is equal to 3y plus 2x minus 1. You're just you're using inductive reasoning, kind of. Oh, not with very few examples. Y equals that is an equation for a line. So you might assume that to get a line in 3 dimensions, all you have to do is add an extra variable. A lot of times that seems to be the way that would work. But what is this an equation for? It's not a line. So that turns out to be the equation for a plane. So it's not. That's the wrong assumption. Okay, you'd be wrong if you assumed that. Okay, wrong. This is the equation for a plane. So for you pick an x and y, so you've got three-dimensional space. Let me draw a three-dimensional coordinate system here. So usually it looks something like this, where you have these two, and then you have a third dimension go out in this direction. So this is x and y. Well, let's make x and y be the ones here. So this is, say that's x and that's y. What you do is you go to some value of x and y, and then you go up a certain amount or down a certain amount, and that defines a point on the plane. And for every value of x and y, there's going to be a z value, and that's the height of the plane above or below the xy plane. This is the z plane. This is the z coordinate. So you can kind of see why that would actually be the equation for a plane. If you take Calc 3, you deal with this stuff a lot. And the equation for a line in 3 dimensions is a parametric equation. So you have x equals some function of t, y is some function of t, and z is some function of t. Now there is a way of eliminating the parameter, but it really isn't. It doesn't allow you to plot the function that much. So if you ever take Calc 3, you'll see what I'm talking about. So that's another example of where parametric equations are important. Drawing lines in three-dimensional space, which is not that, that happens a fair amount. So what I'm going to do is I'm going to just show you something. So this is my free three-dimensional, or my free plotting program, and you can do three-dimensional plots. So here it is. So you see I've got, in this case, x, y, and z. And if I go to let's see what they do. Yeah, so what we have here is z is a function of x and y. What this will do is it'll define a plane. So let me just plot it out. Okay, so there, that's pretty cool, right? So this is not a plane because it's not z equals something x plus something y plus a constant. It's some more complicated function. And so but it's a surface. For each value of z, there's a unique value of x. But for each x and y value, there's a unique value of z. Okay, so that's what you would get if you did. Now, if all I did was, instead of having that fancy equation, if I just said it was going to be equal to 3x minus 4y plus 1, let's see what that looks like. And so that is, there's some way of panning on this thing. How do you do that? Rotate. Just use your arrow keys. Let's try that. Yeah, so there's the plane. So, it doesn't look like it here because it's on its side, but you can see as you rotate around, you can see it's a flat surface. That's your plane. Okay, let's clear that. Let's try. Now if I go to this equation parametric, now you can have a fancy curve parametrically. Let's just see what this looks like. Yeah, well, there you go. That's a sphere. Okay, so apparently that's the parametric equation for a sphere, 3 dimensions. What I'm trying to show you, what I'm finally getting to here, is when we just do a straight line. So we're going to do a parametric equation. So here for x, I'm going to put in 3t plus 1, and for y, I'm going to put in negative 2t plus minus 2, and t minus 5. Now notice there's also you can have 2 parameters if you want to, but we're only using 1 parameter. And there it is. Okay, so there's my line. Just a straight line. So you can see it does actually become a line in 3-dimensional space. So I wasn't lying about the lion. Okay. So why do we use parametric equations? Well, in physics, time is the independent variable. It's the parameter. And x and y are the dependent variables. That's the trajectory. We could have x, y, and z as being the parameters. I mean the coordinates. It also does cool looking curves, right? And much more exciting than what we could do in algebra. And it deals with lines in 3 dimensions, which is extremely important for Calc 3. Okay, so now we're going to just practice a few little things. We've done this kind of before. This is another, for some reason they do them horizontally sometimes. So what you would have is you'd have, instead of vertical table, it's a horizontal table. So you would have t, x, and y. One difficult part is figuring out what is t. Let me go back to my curve. Let me go back to my thing here. We'll go to 2-dimensional parametric equations instead of 3 dimensions. So those are easy to look at. So if I go to equation parametric, you'll notice it says f of t, which is the x coordinate, and g of t, which is the y coordinate. And then you have to actually specify what t is, which is more difficult than when you used to plot x versus y. They always did those things automatically. Yep. It can't do 3 dimensions. It can do parametric equations, which we'll talk about in just a second. But so you do have to put a little more work into figuring out parametric equations, and you really don't know sometimes what t values make the most sense. So I'm just going to pick some t values. I'm going to start at -2, -1, 0, 1, 2, 3, 4. So x is t plus 1, which is going to be -1, 0, 1, 2, 3. So I'm just adding 1 to t. And y is t squared. So this will be 4, 1, 0, 1, 4, 9, 16. And then you can plot it by just getting a piece of graph paper out. So let me find a piece of graph paper. And I won't be able to plot the last point because it's outside of my graph, but we'll go from 10 to -10 here, and -10 to 10 this direction. So I've got just plotting like we normally do, -1, 4, that's that point. 0, -1, 1, 2, 2. Wait a second. Did I do something wrong? I don't think so. Okay, let's go back here. So we got, let me make sure I've done this right. -1, 4, 0, 1. I don't know why I went to -1. So 0, 1 right there. Then you have, yeah, I was plotting the wrong, I was looking at the wrong stuff here. Let me try it again. Okay, so you've got 0, 1, then you've got 1, 0. You've got 2, 1. It's because it's the opposite direction. You know, it's this way instead of looking down. It's throwing me off. Okay, then you've got 2, 1. You've got 3, 4. You've got 4, 9. And if I did -2, I probably have this point right there. Okay, and if I plot those, you'll see I get a parabola. Not a very nice parabola because I can't draw. It's hard to draw that. Okay, so that's the curve. This is the parametric form of a parabola with the vertex at x equals 1, y equals 0. Now, to do this on your calculator, so go ahead and pull out your calculator, and I'll put it on the overhead thing over here. I keep meaning to ask him, what am I doing wrong for this thing? Because it always seems to be hard to see actually using this thing. There's got to be a better way. What if there's another light button here? Yeah. So that's too dark, and then when you put the light on, where's the light? Oh, I didn't want that. Quit. There we go. Then I turn the light on, and it's like, I can't see anything. You can see the buttons, but you can't see the screen. Anyway, what you'll do is you'll go to second XY, you know, like you normally plots. Well, not second. You don't need to do that. Just go to X, Y equals something. You'll notice, well, for mine right now, you can't see it because it's overloaded here. This is in rectangular coordinates. So we need to change it. So let's go back, go back to the main screen, and go to mode. And you'll see mine's in function. So PAR is parametric, POL is polar, SEQ is sequence. So we want to do parametric as our form. So then quit, and then go to Y equals. So what you'll see now is, one thing is the variable has now changed to t instead of x or y. And you can plot, I don't know how many parametric equations here. How many can you go up to? 6 parametric equations. So each one has an x value and a y value. And well, now it's, but before we do that, I want you to go to Window. Before you put in the equations in, go to Window. And you'll see that you have this interface, T minimum, T max, T step, x min, x max, x, what the heck does that mean? I don't know what that means. What the x, well, let's just put in, let's use the values that we just used. So we're going to use -2 for t min, and let's use 3 instead of 4 for t max, and the step, let's use 0.1. So that's our increment. I think these are your x and y coordinates as far as for your plot. So I'm going to put -10 and +10, and x scale, I'll put 1. Y minimum we'll put as -10. Y max is +10. Y scale is 1. I think that's all there is. Yep. Okay. So that's our window. That just sets our values of t and also sets the size of the window. Now we can go back to y, and we'll put in our equation, which was x was equal to t. So where you used to push x, you push t right there where my finger is. And then so it's t plus 1. And then for y, we're going to put in, let's clear that. We'll put in t squared. T squared. Okay, so we have t plus 1 and t squared. That's our equation, and then we graph it. And there it is. Looks like that. And it only shows as much of the curve as you have specified t. So if we want to make the curve, it's only got part of the parabola. If we wanted to get more of the parabola, we probably would go back to window and choose t min to be -3 instead of -2, maybe. Let's see what happens there. And then graph it. So there you can see you get the rest of the plot. So if you don't pick t with a wide enough window or wide enough interval, then you're not going to see the whole plot. Now, let's do another one while we're already on this. Let's go back to y equals and clear both of those. Let's do the circle plot. So if we go and we put in for x, if we put in, let's see, 7 cosine of t for x and 7 sine of t for y, and we should be okay with well, we got to check our parameters, so we need to go to window, and so we'll go from 0 to approximately 2 pi, which is going to be 6.3 in steps of 0.1. The scale for the plot's the same, and now if I push graph, I get a circle. Now it looks like an ellipse because we have to zoom square, I guess, right? So if you get it so that it's square, it looks like a circle. Okay, so that's how they work. So you can do parametric equations on your calculator, but you can't do three-dimensional stuff. You don't do two-dimensional stuff. Okay, so here's another example of eliminating the parameter. So again, I have to solve one of these for t. So the way you would do that is you would take the natural log of x is equal to the natural log of e to the t, which says the natural log of x equals t. And then I plug that into my second equation. So I get y is equal to e to the 3 times the natural log of x. Sorry. So t is the natural log of x. And that's equal to, I was going to do the wrong thing and see if you noticed or not, but what would I do wrong? What do I have to do to this before I can use the inverse properties of exponents and logarithms? Margaret, what do we have to do? So we're looking at this one right here. So it's not 3 times the natural log of x. Yeah, you have to move it inside. It's kind of like with when we used to do the, what was that called? integrating factor. Yeah. Always have to remember to, so you'd have to do this first. That'd be the natural log of x cubed. So now you can do it. So you get the e to the natural log of x cubed is just x cubed. So that would be the rectangular form, which is just a, it's something that looks like that. So this is the parametric form. And if you did that on your calculator, you could do this one, you could do that one, you get the same curve. You'd have to make sure you specify t correctly. Okay, yeah, this is what this, let me put this so you don't get intimidated by all the work there. So what this is to show that if you have 2 points, so in algebra, if you want to find the equation for the line given two points on that line, what you do is you use the point slope form of the linear equation and then solve for y to get it into the slope intercept form. But it turns out that the equivalent parametric form of the point slope form of the linear equation, in this case there is no slope, is that x is equal to, so you take those 2 points and you can define 2 parametric equations, one for x and one for y, based on the values for the 2 x and y coordinates. So x equals x1 plus t times x2 minus x1, and y is equal to y1 plus t times y2 minus 1. And it really, like with anything that involves lines, you could also, let me see if I can have room in here to, no I can't, I'll do it on top. We could have also done this. You could have chosen x2 to be the, you could switch them, in other words. Both of these would work. Y equals y2 plus t times y1 minus y2. So it doesn't matter which one you choose is the one that's in the parentheses and out of the parentheses. Either one's okay. So what I'm going to show you is use eliminating the parameter to show that these are equivalent to the point slope form of the linear equation. So the first thing you can do is you can solve this one for t. So what you'll get is x minus x1 and then divide by x2 minus x1. So all I'm doing is solving for t just like I solved for t over here. And also remember the slope, we'll use this later, the slope is y2 minus y1 over x2 minus x1. So once I've solved this equation for t, I can plug it into the second equation. So now here's the second equation. So I've got y1 plus, instead of t, I'm using what I solved for t from the first equation. So I'll get this expression, x minus x1 over x2 minus x1 times y2 minus y1, but y2 minus y1 over x2 minus x1 is the slope. So what I'm doing here is I'm just grouping these two together. So instead of it being the denominator here, I'm making it the denominator there. And at that point, you can replace it with the slope, and you get that. And if you, you can also rewrite this as that, which is this is the, if I move this to the left-hand side, I come up with the point slope form of the linear equation. So this is the rectangular form, and that's the parametric form. Given 2 points, the one advantage of this one is I don't have to calculate the slope at all. I can just use these equations directly. So if I went to this graphing program, I'll come back in a second. So if I wanted to plot a line, all I'd have to do is, I want it to go through the points. I'm going to pick 2 points. Let's just see what happens here. So I'm going to pick 2 points. So I want a line that goes through 2, 1 and -1, -3. Okay. So that's the two, and I could find the slope of these, the slope between these 2 points, plug it in here, choose either this one or this one as x1 and y1. Or the parametric form would be x is equal to 2 plus t times x2, which is -1 minus 2. So I'm using this equation. Let's put x1, y1, x2, y2. Okay, so we have x1 plus t times x2 minus x1, so that makes sense. And then you have y is equal to y1, which is 1, plus t times y2 minus y1. And you can simplify that down to 2 minus 3t and 1 minus 4t. So those are my parametric equations. And if I do that, 2 minus 3t, 2 minus 3t, and 1 minus 4t, and I've got to choose some values here for t, so I'm going to pick -8 to +10. I don't know why, but I did, and there you go. Okay, so there's your line, and you'll see that, does it go through point 2, comma 1? Yes. Does it go through point -1, comma -3? -1, well, it's off the screen, but it does. Okay, so it works. So that's just demonstrating two things. It's demonstrating how you can have linear equations in parametric form based on the coordinates of 2 points, and also how you can use eliminating the parameter to get to the rectangular form of the equation. And I'm going to, we'll do a few more things, but I'm going to assign the homework for section 2 now. So that's it for today.